work distributions, we can measure and observe those. But if we go down even further and really we want to think about trajectories. So each realization of this experiment, there's a particular initial state, and there's a particular microscopic trajectory that the system follows through phase space. And for the reverse process, first protocol, first experiment, there's, in principle, the system can follow exactly the reversed trajectory. And the probability of the reversed, time reversed trajectory to the forward trajectory is related by the exponential of the dissipation, by the exponential of the total change in entropy. So entropy doesn't just qualitatively determine which direction time is flowing. We think, you know, the direction of the future is the direction of time where entropy is increasing. But in these small systems, you do the experiment, and again, we think about, I'll give you a little movie. I'll give you a little movie of the experiment. I'll show you this trajectory. Can you tell whether I'm showing the movie of this experiment in the forward direction, or if I reverse the movie and I'm showing it in the opposite direction? And it's going to be ambiguous, because the magnitude of these little systems, the magnitude of this dissipation is going to be within an order or so of kT. You can't say absolutely with certainty which way the movie should be running. But you can say with, you know, that it's probably going to be in the direction that the entropy is increasing. So it's not just that a qualitative entropy is what breaks time reversal symmetry, that's what gives us an arrow of time. On this microscopic level, it's a quantitative relationship between the forward and reverse ensemble of trajectories. So why is that true? It really is embedded already. We didn't invent actually any new physics. It's really already embedded in what we already knew about equilibrium statistical mechanics. And there's sort of two important properties that combine to give us this relation. One is this, that a system in equilibrium, the probability of a particular microstate, and we have this environment, which this thermal environment which the system is equilibrated with. That's because it's always easier to mathematically treat a canonical ensemble than a microcanonical ensemble. So we know that at equilibrium, the probability of any particular microstate is just going to be, well, it's going to go kT, and there's a free energy in here, which sort of normalizes the probability distribution. And then it just goes by the energy of the microstate. Now, note there's a temperature in these relationships. There's a temperature in this equilibrium relation. There's also a temperature in those non-equilibrium relations. Now, that sounds a bit iffy. Temperature is really only well-defined for a macroscopic equilibrium system. And many people have attempted to extend the idea of temperature to non-equilibrium systems, but I think it's fair to say there's no broadly agreed non-equilibrium temperature. The trick is that the temperature that appears in these relationships is not the temperature of the system, it's the temperature of the environment. And the reason is that there's the entropy change, there's sort of an entropy change of the system itself, but there's also an entropy change in the environment. We dump a certain amount of heat into the environment, and that is what, and the amount of entropy, given the amount of heat we put in, is determined by that temperature. So it's always the temperature of the environment, and we completely circumvent this problem of having to define a non-equilibrium temperature. The other really important concept is this idea of microscopic reversibility. Now, we use words differently in different fields and even different parts of physics. And I've often found myself used to have these really weird conversations where clearly I was totally talking past, people were just totally talking past each other. And this often turned out to be that we were using the same word to mean subtly different things, coming from slightly different areas of physics. So people have often used reversibility, reversible dynamics in the last few days to mean a dynamics that is invertible. So I have, say, a Hamiltonian dynamics of an isolated system. I start in a particular state, I let it evolve over some point in time, I come to a definite final state, and I reverse the clock, and I'll come back to exactly the same place. Now, I don't care. That turns out not to be what I care about. Invertibility is neither necessary nor sufficient. What actually matters is that the probability of a particular path and its time reverse path is the same. So that encompassed, I can think about Hamiltonian dynamics is fine. That also encompasses then any kind of stochastic dynamics, because I'm really often thinking about I'm really only looking at the system, and there's a whole environment that I've sort of traced out, and that makes the dynamics of the actual system I'm looking at stochastic. So it's invertibility is not, in fact, sufficient. There are these thermostated deterministic dynamics, Nose-Hoover thermostat in molecular dynamics. If you take one of these deterministic dynamics on the computer and you start beating on it, driving it out of equilibrium, you actually get a compression of phase space. So although it's invertible in the sense of I had arbitrary precision, I could run the dynamics back and go back to the same place. This compression of phase space means that the phase space volumes at the two ends of my trajectory are not the same. So it's, that doesn't count. That's actually a non-equilibrium system. So being in or out of equilibrium is not a property of the system. It's a property of the ensemble from which the system was sampled from. So I could sample from an equilibrium system, and I give you this, or I could beat up on the system for a little while. There's a non-equilibrium probability distribution. I could give you that. So you can't say with certainty just by looking at the microscopic realization of the system whether it came from equilibrium or not. The system itself does not know, which means that suppose I beat up on the system for a little while, it's out of equilibrium as an ensemble as a whole. Now I just let it coast for a little while. Its behavior has to be the same as if it was, in fact, sampled from an equilibrium distribution. And that actually strongly constrains the non-equilibrium dynamics. And we get all these wonderful properties about this is how non-equilibrium statistical dynamics works. It's all about breaking time reversal symmetry at the level trajectories. So where's this relevant? Again, I think it becomes very relevant when we start thinking about molecular scale machines, either in biology or the kind of nanotech machines we would really like to be able to build ourselves. I'm involved in my day job, as you say, in the lab. We're very interested in alternative energy, particularly from the sun. So we would like to build an artificial photosynthetic system that will take sunlight and turn it into a usable hydrocarbon fuel you can stick in your gas engine. And so that means when we're going to be operating building these nanotech devices, hopefully out of solid state materials rather than rather delicate organic materials, we face the same problems that biology does. And that is that we're operating down here on single photons or single molecules, and we're not that far above the thermal threshold. So for example, this is the photosynthetic reaction center. And one of the things that any molecular scale machine, right, has to do is it has to continuously break time reversal symmetry. I need to do something useful. I can't just spin forward and back. I have to continuously spin in the direction of doing something that I actually want to do. And so in this example, a photon comes in, we capture the photon very efficiently, but then we have to use that to do a charge separation. And we've got to get the charge separated a long way quickly. We don't want it recombining. It's also useful to realize that biology is not really trying to be efficient. Thermodynamic efficiency is not its first order of business. We're talking about those E. coli experiments. The winners are not the bugs that are efficient with their food. They're the ones that grab as much food as possible before their neighbors do. So the object of the exercise is not as a first order thing to be efficient, it's to be fast. Probably maybe its power output is the right thing to think about being optimized. And so we have to split this charge. We can't have this charges coming back together because then you'd get a high energy photon coming off and you'd lose it to the environment. Or worse, it will blow your photosynthetic reaction center to pieces. It turns out one of the huge design constraints on nature for this thing is that the center of this reaction center falls to pieces on the order of minutes and has to be continuously repaired, which is one reason that we think we have to go to solid state materials. We could build this kind of thing out of organic materials. We just don't have the ability to do that continuous repair that nature does, whereas we can build inorganic materials that do this, hopefully, much more robustly. So there is a loss in energy here of about 10 kT, ballpark. And that sort of, you can think about the cost of having to lock in this charge separation. This is the cost, somehow, of having to break time reversal symmetry. So there's all sorts of fun things we can do to try to tease out these relationships. I'm just briefly going to sort of discuss a couple of ways that trying to think about this. There's fundamentally a trade-off then between the efficiency and breaking time reversal symmetry. You don't want to waste all your energy, but you have to spend some of it in order to actually get anything done. So one of the nice things is that I don't know how to measure entropy once we're out of equilibrium, which is very irritating. But we can measure all sorts of entropic measures if what we're measuring is an entropy relative between two ensembles of trajectories, between the forward ensemble and the reverse ensemble. And one of the nice things that comes out is the average dissipation is actually just the relative entropy between the forward ensemble and the reverse ensemble. And so we add up the dissipation on both directions, we basically get the hysteresis. The hysteresis is really just the Jeffreys divergence between the forward ensemble of trajectories and the reverse ensemble. And there's all sorts of fun things we can then play with information theory. This is another way of sort of trying to analyze that same data. So imagine the following game. I do the experiment, I show you this molecular detailed movie, and I ask you which way were you running the experiment for real? Were you really doing the expansion or the contraction? And the average amount of information, that's a 1-bit thing, right? It's either this way or that way, 1 bit. So the average amount of information you obtain from a single realization of the experiment is encompassed by this particular Jensen-Shannon divergence measure. So it's either, if the thing's perfectly reversible, you get 0 bits, and if it's perfectly irreversible, you get 1 bit. So this is just, again, it's just a different way of trying to tease out this trade-off between breaking time reversal symmetry and dissipation. Now notice that I keep talking about these movies. Maybe we've got every single molecular detail, and none of that matters. So in statistics terms, the sufficient statistic is the work, or more broadly speaking, it's the dissipation, if you want to determine which way the time's flowing these things. And so the idea is that there is a trade-off, as I said. So it turns out you can start making, talking about the trade-off between this time asymmetry, how much you break time symmetry in a particular realization of a process, and how much you had to dissipate in KT. There's an area there's a lower bound, so you have to, if you want to strongly break time asymmetry, you have to burn about 10 KT. You don't need to burn more than 10 KT. If your process is burning more than 10 KT per cycle, it's probably wasting energy. So, one way of looking at this is sort of a 250 millielectron volts overpotential. In catalysis, people often talk about the overpotential. It should be enough for most situations. And then instead of thinking about efficient versus inefficient, you can more think about effective. Am I effectively using this dissipation? I've got to dissipate something. But if I'm way up over here, I'm just wasting energy. I'm just dissipating energy into the environment, and I'm not using it to actually break the time symmetry and actually move myself along. Life wants tomorrow to look different from today. The whole point is to continuously break time symmetry and avoid thermodynamic equilibrium. So that's the sort of, those are the sort of the key thoughts I'd like you to take away. That there is the entropy change quantitatively is what breaks time reversal symmetry at the level of trajectories, and that on a broader level then there's this trade-off between thermodynamic efficiency and time symmetry breaking. And this is relevant to, this is a cartoon of the sort of photosynthetic artificial reaction things that we would like to build. Thank you.